Light reaching the James Webb Space Telescope left its source before the Earth existed. It has been in transit for more than 13 billion years. In May 2024, Webb confirmed the most distant galaxy ever seen, formed only 290 million years after the Big Bang. It already held oxygen. Dead stars make oxygen. A stellar generation had lived and died before it appeared. That should not be possible. On Christmas Day 2021, that changed. What Webb found was not the quiet infant cosmos, and most of it lies permanently beyond reach. We trace what Webb uncovered, confront what it broke, and face the silence at the edge of sight. Subscribe and leave a like if this science matters to you. That light has been traveling since before our solar system existed. Let us see what it carried. When you look up at the night sky, you are not seeing the universe as it is. You are seeing the universe as it was. A vast collection of messages sent at different moments in the past, all arriving at your eyes simultaneously, none of them current. This is not a poetic way of thinking about starlight. It is a precise description of what is actually happening. Light travels at roughly 300,000 kilometers per second, fast enough to circle the entire Earth more than 7 times in a single second, fast enough that at human scales, it seems to arrive the instant it leaves its source. But the universe operates on scales so far beyond human experience that even this speed cannot eliminate the delay between departure and arrival. That delay is always there. The further the source, and the longer the journey, the older the information when it reaches you. Begin close to home. When you look at the moon, the light entering your eyes left its surface about 1¼ seconds ago. The moon you see is not the moon as it exists at this moment. It is the moon as it was a heartbeat in the past. The difference is too small to matter, but it is real. Look at the sun, and the delay stretches to roughly 8 minutes. The sunlight warming your skin was emitted from the solar surface 8 minutes ago. If the sun were to vanish at this precise instant, you would not know for 8 minutes. The sky would still be blue. The light would still be coming, and then it would stop, move further out, and the delays become something the human mind struggles to hold. The nearest star beyond our own, Proxima Centauri, and appears to us as it was more than 4 years ago. When astronomers train their instruments on the center of the Milky Way, the light arriving has been traveling for roughly 26,000 years. It left the galactic center before the earliest human civilizations, before agriculture, before any written language. The sky over ancient Babylon still carried that same light, still in transit, still millennia from completing its journey. And when you look at the Andromeda Galaxy, that faint smear visible to the naked eye in a dark sky, the most distant object most people will ever see without a telescope. The photons reaching your eyes began their journey 2.5 million years ago. 2.5 million years. At that moment, our ancestors were using stone tools on the African savanna. The human species as we know it did not yet exist. That light has been crossing the universe since before we were here to receive it. Think about that for a moment. Every object in the night sky is a window into a different era. The sky is not a photograph of the present. It is something closer to a museum of different ages, every exhibit lit by light that departed at a different point in history. Some from centuries ago, some from millions of years ago, and some, as telescopes have grown more powerful, from billions of years ago, from epochs when the universe itself was young. Now consider what happens to that ancient light as it travels. The universe is expanding. Space itself is stretching. And when space stretches, it stretches everything moving through it, including light. A beam of light emitted in the very early universe does not arrive here with the same wavelength it had when it left. The expansion has been pulling at it for billions of years, shifting it from energetic ultraviolet toward visible light, and then past visible light into the infrared. This effect is called redshift. It means that the further back in time you look, the more dramatically the light has been transformed. The earliest galaxies in the universe do not glow in any color the eye can detect. Their light has been stretched beyond the visible spectrum entirely. There is a limit to how far back any observation can reach, and it is not a technological one. 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before that moment, the cosmos was so hot and so dense that light could not travel freely. It was constantly scattered, trapped in an opaque plasma. When those atoms formed, the light imprisoned in that plasma was suddenly released. Those photons have been traveling ever since, and they are the oldest light that exists. In 1965, two physicists working at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to trace an inexplicable hiss in their radio antenna, a noise that came with equal strength from every direction in the sky. They cleaned the antenna, they checked their equipment, they chased away pigeons nesting inside the horn. The hiss remained. What Penzias and Wilson had stumbled onto, without looking for it, was the afterglow of the Big Bang itself, a faint bath of microwave radiation filling the entire universe, the relic of that moment when light was first set free. They received the Nobel Prize in Physics for the discovery 13 years later. The cosmic microwave background is a snapshot of the universe at 380,000 years old. It is as far back as any photon-based observation can ever reach. Beyond it lies an era permanently dark to any telescope. Not because instruments are too weak, but because no light from that era survived to reach us. Everything that came after, every galaxy, every star, every photon that has ever arrived at a human eye or instrument, exists between that moment and the present day. That span contains 13.8 billion years of cosmic history. And for most of the time, humans have possessed instruments powerful enough to explore it. A large portion of that history remained hidden, not because it was empty, but because the light carrying its story had changed in a way that most telescopes were simply not built to follow. In the spring of 1995, astronomers made a decision that seemed, to many of their colleagues, almost reckless. They pointed the Hubble Space Telescope at a small patch of sky in the constellation Ursa Major, a region that appeared to contain almost nothing, chosen precisely because it was empty of anything bright enough to interfere. And they held it there for 10 consecutive days. 150 orbits. More than 100 hours of observing time, all directed at a piece of sky that looked, to the naked eye and to every previous instrument, like simple darkness. What came back was not darkness. Nearly 3,000 galaxies appeared in that image, each one a gravitationally bound island of stars, each one occupying a region of the sky so small that the entire patch could be covered by a grain of sand held at arm's length. Astronomers had suspected the deep universe contained more than it seemed to, but the number was still startling. 2 years later, a second deep field, this time in the southern sky, revealed much the same. The universe, wherever Hubble looked deeply enough, was full. A few years after that first deep field, Garth Illingworth and his colleagues began pushing further, combining Hubble observations across multiple campaigns to build ever deeper views of the early cosmos. Staring at those images was like excavating a site layer by layer, each additional hour of exposure revealing galaxies further back in time. Fainter, redder, more distant. The data kept showing structure where emptiness had been expected. By the early years of the 21st century, the combined Hubble Deep Field programs had revealed nearly 10,000 galaxies in a single sky patch the size of that same grain of sand. But Hubble's power came with a fundamental constraint, one written into its design. It was built to see the universe in visible light and near-infrared wavelengths, the kind of light human eyes evolved to detect, the kind that traces the stars and gas of relatively nearby galaxies with extraordinary clarity. For the science it was designed to do, this was exactly right. For the science astronomers increasingly needed to do, it would prove to be a wall. The problem was redshift. Recall what we established earlier. The further back in time you look, the more the universe's expansion has stretched the light from its sources. A galaxy seen 1 billion years after the Big Bang has had its light stretched considerably. A galaxy seen 200 million years after the Big Bang, the kind of object that might reveal what the earliest cosmic structures actually looked like, has had its ultraviolet radiation stretched so severely that it arrives as infrared. Hubble could not see infrared, not properly, not deeply. The earliest galaxies were not absent from the universe, they were absent from Hubble's images, which was a very different thing. Astronomers devised workarounds. One of the most elegant was the Lyman break technique, a method of identifying distant galaxy candidates by looking for a sharp drop in their light at a specific wavelength, the point at which neutral hydrogen absorbs ultraviolet photons almost completely. A galaxy at high redshift would appear to vanish entirely when observed through certain filters, as though the light had simply been switched off at that wavelength. This dropout signature could be used to identify candidates quickly, in large numbers, using the instruments already available. It was clever, efficient, and widely used. It was also imprecise in a particular way. The Lyman break technique could find candidates. It could not confirm them. To know with certainty how far away a galaxy was required something more demanding. Spectroscopy, the process of spreading its light into a spectrum and reading the exact pattern of wavelengths to determine the redshift directly. Spectroscopy was slow. It required long exposure times and larger instruments than Hubble could provide for the faintest objects at the greatest distances. For the earliest epochs of cosmic history, it was essentially out of reach. The Spitzer Space Telescope, launched in 2003, opened a partial door. Where Hubble operated mainly in visible light, Spitzer was built to observe in the infrared, and it extended the reach of galaxy surveys into wavelength ranges Hubble could not access. Ivo Labbé and other researchers used Spitzer to begin characterizing the earliest galaxy populations, measuring their approximate brightness, estimating their stellar masses, building the first rough portrait of what the early universe might contain. The work was painstaking and the results tantalizing, but Spitzer's mirror was less than a meter across. Its resolution was limited. It could hint at what was there. It could not resolve it. From Hubble's launch in 1990 to the release of Webb's first science images in 2022, 32 years passed. During that time, astronomers assembled a picture of the early universe that was genuine and hard-won, but which they increasingly suspected was incomplete in a specific and important way. The tools they had were built for the wrong part of the spectrum. The light they needed to follow had moved beyond their reach. What was needed was not an adaptation of an existing telescope. It was something new. An instrument designed from the outset for infrared light, with a mirror large enough to collect the faintest ancient photons and a thermal architecture cold enough not to drown them out. Engineering a machine like that would require solving problems that had never been solved before. Here is the problem. To detect infrared light, you must be colder than the source of the infrared light you are trying to detect. This is not an engineering preference. It is a physical law. If the telescope you are trying to build is warm, it will glow in precisely the wavelengths you are trying to observe, drowning out the faint ancient signals you are reaching for. The telescope would be blinding itself. Think of a photographer trying to work in a dark room while holding a lit torch. The torch does not help. It ruins everything. The only solution is to extinguish it, to become, as far as the infrared spectrum is concerned, invisible, to be cold enough that the instrument stops emitting in the very wavelengths it needs to receive. For the James Webb Space Telescope, this meant getting cold, very cold, the kind of cold that does not exist naturally anywhere on Earth. The solution was a sun shield, 5 layers of a reflective plastic film, each layer thinner than human hair, stacked at precise intervals and separated by the vacuum of space. The layers work together as a thermal barrier of extraordinary effectiveness. On the side facing the sun, the shield reaches temperatures of roughly 230 degrees Celsius. On the shaded side, where the telescope lives, it drops to minus 230 degrees. When fully deployed, the shield spans an area comparable to a tennis court. It is the most consequential piece of engineering on the observatory. Keeping the telescope cold also dictated where it had to go, and Webb orbits a point in space called the second Sun-Earth Lagrange point, a gravitational balance point that sits 1.5 million kilometers from Earth, in the direction directly away from the Sun. At that position, the telescope can orient its sunshield permanently between itself and both the Sun and Earth, remaining in thermal equilibrium indefinitely, never drifting into sunlight. Once the cold side of the telescope reached its operating temperature, the next challenge was the mirror. Webb needed to collect infrared light from objects so dim that a single photon every few minutes might represent a meaningful signal. That required a mirror large enough to gather light from an enormous area of sky. Webb's primary mirror spans 6.5 meters across, more than twice the diameter of Hubble's, and it is composed of 18 hexagonal segments, each one machined with extreme precision from a metal called beryllium. Beryllium was chosen for a reason that matters enormously at operating temperature. Most materials change shape significantly as they cool. Beryllium barely does. When Webb is cooled from room temperature down to its operating temperature of minus 230 degrees, the 18 mirror segments shift only imperceptibly in shape and dimension. That stability is not optional. The segments must fit together so precisely that they function as a single continuous surface, and they must do so reliably in deep space without anyone available to adjust them by hand. Each segment is coated in a layer of gold roughly 1,000 atoms thick. Gold reflects infrared light with exceptional efficiency. Behind the mirror, 4 scientific instruments sit at the telescope's focus, each built for a different task, each contributing something the others cannot. The primary imaging camera was built by a team at the University of Arizona, led by Marcia Ricci. It captures light across wavelengths from the edge of visible red through the near-infrared, making it Webb's main eye on the early universe. It is also the instrument responsible for the telescope's own alignment, measuring the wavefront of incoming light to detect any imperfections in the mirror, then guiding the adjustments that correct them, down to increments of 10 nanometers. 10 nanometers is roughly the diameter of a small protein molecule. The spectrograph was built by the European Space Agency under the scientific leadership of Pierre Ferrouille. Where the imaging camera takes pictures, the spectrograph spreads light into its component wavelengths, revealing the chemical fingerprint of whatever it is observing. What makes it extraordinary is its capacity. It can take spectra of up to 200 individual objects at the same time. It achieves this through a microshutter array, a grid containing 248,000 tiny doors, each one smaller than the width of a human hair, each one individually controlled by an electromagnet. Doors over background sky stay closed, doors over targets of interest open, admitting light from only those sources. The array had never been flown in space before. The mid-infrared instrument was built by a European consortium led by Gillian Wright at the United Kingdom Astronomy Technology Centre, working alongside a team at NASA's Jet Propulsion Laboratory. It operates at wavelengths beyond what the other instruments can reach and must be cooled even further, to minus 266 degrees Celsius, using a dedicated cryogenic cooler. It is, by a significant margin, the coldest operational science instrument ever flown in space. The fourth instrument, a guidance and spectroscopy system contributed by the Canadian Space Agency and led by René Doyon at the Université de Montréal, keeps the telescope locked precisely on its targets, while also providing additional spectroscopic capability. Without it, Webb could not maintain the pointing stability that long observations require. It was Lee Feinberg, working at NASA's Goddard Space Flight Center, who served as the optical telescope element manager, the person responsible for overseeing the mirror system through years of design, fabrication, testing, and integration. He watched each of the 18 segments come together. He watched the observatory go through environmental testing, vibration tests, acoustic tests, thermal tests. He watched it survive each one. In July 2011, Congress almost stopped him. A House Appropriations Subcommittee voted to terminate the Webb program entirely, citing years of cost overruns and schedule delays. The Senate restored the funding. The committee that would eventually change our picture of the early cosmos came within a single legislative vote of never existing. By the time the telescope completed its final integration tests in 2021, it had taken more than 3 decades, involved thousands of scientists and engineers across 15 countries, and cost roughly $10 billion. Everything it was, every mirror segment, every cooled detector, every tiny door in the microshutter array, was folded up inside the nose cone of a rocket, waiting for a morning in late December to find out if it would work. It was Christmas morning, 2021. At the Guyana Space Center in Kourou, French Guiana, the final countdown was running. Inside the nose cone of an Ariane 5 rocket, the James Webb Space Telescope sat folded into itself, mirror wings tucked in, sun shield compressed, every instrument in its launch configuration, and waited. At 12 minutes past noon, the coordinated universal time, the rocket lifted off. 27 minutes later, Webb separated from the rocket's upper stage and began its journey alone. No human being had ever been where it was going. No repair mission could follow if something went wrong. From the moment of separation, the telescope was on its own. Before the deployment sequence began, it helps to know what the engineering team was carrying in the back of their minds. Before launch, NASA engineers had catalogued 344 individual mechanisms that would need to work correctly, in sequence, for the telescope to reach full operation. Latches, hinges, motors, bolts, folded membranes, each one a single point of failure, each one capable, if it failed, of ending the mission entirely. 344 things that had to go right, one after another, with no possibility of intervention from the ground beyond, sending commands and hoping. 3 days after launch, the sunshield deployment began. The 5 Kapton membranes had been folded like an impossibly delicate origami into the launch configuration. Now, guided by commands sent from a control room 400,000 kilometers away, the pallets that held them began to lower. Telescoping booms extended outward. The membranes unfolded, layer by layer, until all 5 were spread across the void. Then they were pulled taut, stretched to their full extent. The barriers between the telescope and the sun locked into place. Each step of this process had been rehearsed thousands of times on the ground. None of that rehearsal fully addressed the fact that space is not the ground. Vibration, thermal contraction, the absence of gravity. Any of these could cause a mechanism that had performed perfectly in testing to fail in flight. The team watching from Earth could see telemetry. They could not touch anything. The sunshield held. On January 7th and 8th of 2022, the 2 wings of the primary mirror swung into position and locked. 18 beryllium segments, each one folded to fit inside the Ariane fairing, now completed the telescope's full hexagonal face. Structurally, the observatory was whole, but the mirrors were not yet aligned. Then came a piece of news that the team had not allowed themselves to expect, and the trajectory corrections that guided Webb to its destination had been executed with extraordinary precision. So accurately that the telescope had consumed far less propellant than the worst-case mission planning had required. The fuel reserves that remained were not a margin. They were a windfall. The operational lifetime of the telescope, initially planned at around 10 years, might extend to 20 or more. The telescope that took 3 decades to build had just been given extra time. On January 24th, Webb arrived at the second Lagrange point, the gravitational balance position 1.5 million kilometers from Earth, and settled into its orbit there. What remained was the hardest part. The 18 mirror segments were individually positioned, but they were not yet functioning as a single mirror. Each one was slightly tilted, slightly offset from its neighbors. The telescope had to learn to see, and this required adjusting each segment with a precision that is difficult to describe in ordinary terms. The actuator motors that moved the mirrors were capable of steps of 10 nanometers. A nanometer is 1/1000th of a meter. 10 nanometers is smaller than most viruses. It is far smaller than any wavelength of visible light. The mirrors had to be aligned to this level of precision, from 1.5 million kilometers away, using only the remote commands sent by the team on Earth and the light from a single bright star. The first alignment target was a star in the constellation Ursa Major, designated HD 84406. The first images of this star, taken before alignment began, showed not one point of light but 18, one for each mirror segment, each slightly offset from the others, creating a scattered constellation of blurry smears where a single sharp point should have been. It was the view of a telescope that did not yet know itself. Keith Parrish, who led the observatory's commissioning as NASA's commissioning manager, later described those first 30 days after launch as action-packed, a continuous sequence of decisions and adjustments, one activity following another without pause. What followed was something different. Months of slow, methodical iteration, each adjustment of each segment guided by what the previous adjustment had revealed. 18 smears, becoming 18 slightly less blurry smears, becoming something that began to resemble a coherent image. It was like tuning 18 separate instruments to the same pitch, one by one, until the chord resolved. On July 11th, 2022, the James Webb Space Telescope's first science images were released to the public. Astronomers around the world had been waiting. Within hours, the The data were being downloaded, analyzed, and interrogated by research teams who had spent years, in some cases entire careers, preparing for this moment. What they found in those images, in the days and weeks that followed, was not what they had expected. The Webb first deep field went public on the morning of July 11, 2022, during a White House briefing hosted by President Biden. It showed a patch of sky smaller than a grain of sand held at arm's length, and within it, thousands of galaxies, layer upon layer, some of them so distant that their light had been traveling for more than 13 billion years. It was the deepest infrared image of the universe ever captured at that resolution. The room at the White House fell quiet when it appeared on the screens. Within hours, research teams around the world were downloading the data. They had not needed to wait for an official release. One of the most significant decisions made about Webb's science program before launch was that certain datasets would become public immediately. Not held back for the teams that designed the observations, but released to the entire scientific community at the moment they were processed. The survey that would prove most consequential in those first weeks had been designed before launch by Stephen Finkelstein and his colleagues at the University of Texas at Austin. It was called the Cosmic Evolution Early Release Science Survey, SEERS, as those in the field came to call it. And its target was the extended Groth Strip, a region of sky that Hubble had already observed extensively. The overlap was deliberate. Astronomers would be able to compare what Webb saw with what Hubble had seen before, in the same patch of sky, using the same region as a shared reference point. In Melbourne, Australia, Ivo Labbé and his team had a specific target in mind. For years, Labbé had been thinking about a class of objects that his group had begun calling, half in jest, ultra-red flattened objects. The name was playful, but the idea behind it was serious. If the very earliest, most massive galaxies existed, objects that had assembled enormous quantities of stars in the first few 100 million years after the Big Bang, they would appear in Webb's infrared images as compact, intensely red sources, distinct from anything in Hubble's catalogue. His team had spent years preparing their search. Within days of the data going public, they began running it. Erica Nelson, working at the University of Colorado, was doing the same. Scanning through the Webb images from the SEERS field, she noticed something. A tiny red dot. Barely resolved, barely there. She flagged it. Labbé looked at it. He ran the photometric analysis, measuring the brightness of the object through multiple filters, fitting the results to models of stellar populations and redshifts, extracting an estimate of the galaxy's distance and mass. The numbers that came back stopped him cold. The galaxy was 13.1 billion light-years away. The universe, when it emitted that light, was less than 700 million years old. Its stellar mass was approximately 100 billion solar masses. You look at that figure, you read it again. 100 billion times the mass of our Sun, assembled in less than 700 million years. Labbé later said he very nearly spilled his coffee. Think about what that number requires. In the modern universe, the process of turning gas into stars is slow and inefficient. The vast majority of gas inside a galaxy never becomes a star at all. It is heated by supernova explosions, stirred by stellar winds, blown outward before it can collapse. Modern galaxies convert only a small fraction of their available gas into stars over their entire lifetimes, typically a few percent. Building a galaxy with 100 billion solar masses in less than 700 million years would require something dramatically different. It would require essentially all of the available gas to become stars almost at once, a conversion efficiency approaching 100%. No mechanism anyone understood could produce that. Labbe extended the search. He and Rachel Bezenson at the University of Pittsburgh, together with Nelson and other colleagues, broadened their analysis across the full dataset, looking for similar objects in the same field. 6 candidates emerged, all of them from the first 500 to 800 million years of the universe's history, all of them with stellar masses at or approaching 100 billion solar masses, all of them under any standard reading of the models that had governed cosmology for 3 decades, physically impossible. The weeks that followed, the team later said, were fun and intense. The analysis had to be impeccable. The result was so unexpected, so far outside the range of what the standard models predicted, that the standard of evidence required was correspondingly higher. Every alternative explanation had to be considered and ruled out. The paper took months to prepare, not because the observations were uncertain, but because the team understood exactly how the result would land when it appeared. Labbe put it plainly. They had discovered the impossible. He qualified it immediately. The observations were real. The measurements were solid. What might need revision was not the data, but the understanding of how galaxies form. When the findings were presented publicly, Garth Illingworth, who had spent decades staring at deep field images from Hubble's earliest campaigns through to Webb's first light, was asked to comment. He did not reach for measured language. "We have a problem," he said, "and it's real. Where the hell did these bright things come from? They weren't in the storybook." Illingworth's question, "Where the hell did these bright things come from?" was not rhetorical. It was a genuine scientific problem. And to understand why it is a problem, you need to understand the framework that Webb had just put under pressure. For 3 decades, cosmologists have operated with a model of the universe that is, by any measure, and one of the most successful theories in the history of science. Its full name is the Lambda Cold Dark Matter Model, which is often shortened in ways that make it sound more like a code than a cosmological framework. Lambda refers to the cosmological constant, the term Einstein introduced to represent dark energy, the force responsible for the accelerating expansion of the universe. Cold dark matter refers to the invisible mass that accounts for the majority of all matter, moving slowly enough in the early universe to clump together under gravity and form the large-scale structures we observe today. Put them together, and you have the standard picture of cosmic history, the scaffolding on which every subsequent observation has been interpreted for a generation. The model made precise predictions about how galaxies form. The process it described was slow, sequential, and governed by the physics of cooling gas. In the earliest universe, tiny fluctuations in the density of dark matter, fluctuations seeded by inflation in the first fraction of a second, began to grow under gravity. Dark matter halos assembled first, pulling ordinary matter into their gravitational wells. That gas had to cool before it could collapse further, and cooling took time. Hundreds of millions of years passed before the densities required to ignite nuclear fusion were reached in enough places for the first stars to form. Then those stars began to build galaxies from the inside out, their light and stellar winds gradually assembling the structures we recognize. It was a picture of the universe constructing itself the way a city gets built. Foundations first, then infrastructure, and then the first modest buildings, everything growing slowly from the bottom up. At 500 million years after the Big Bang, that picture said the universe should have been sparse, fragile, small, chemically bare, the raw material of future galaxies, not the finished product. Webb was sent there to observe this early phase, to confirm and sharpen the picture of cosmic construction at its earliest stages. What it found instead was crowds, bright, massive, fully assembled galaxies, at epochs where the model had predicted almost nothing resembling them. As we saw in the previous chapter, the scale of the discrepancy was significant. Stellar masses approaching 100 billion solar masses in objects that should not have had time to accumulate that much in any configuration the standard model permits. Here is where it gets stranger. Webb's spectrographs did not merely detect these galaxies, they read their light. And in the light of some of those early objects, at epochs only 500 million to 1 billion years after the Big Bang, astronomers found carbon. They found oxygen. These are not primordial elements. They are the products of stellar nucleosynthesis, the heavy atoms forged in stellar cores and dispersed into the surrounding gas by supernova explosions. Carbon and oxygen cannot exist in any meaningful quantity until a star has formed, burned through its fuel, and died. Finding carbon and oxygen in a galaxy 500 million years after the Big Bang does not just mean that galaxy is massive. It means an entire generation of stars had already formed, burned, and exploded before it came into view. And the timeline did not add up. It still does not. P. James Peebles, whose theoretical work decades earlier helped lay the foundations of the lambda cold dark matter framework, and who received the Nobel Prize in Physics for those contributions in 2019, offered a view that represents the most careful and disciplined response to the accumulating evidence. The model, he noted, passes demanding tests that establish it as a good approximation to reality. Every framework in physics has anomalies and open questions. The right response to those anomalies is not to abandon the framework, but to treat them as guides, to look for the additional physics that a better theory would eventually incorporate. Webb's findings in this reading are not evidence that lambda cold dark matter is wrong. They are evidence that it is incomplete, and that distinction matters enormously, and it is honest, but it does not dissolve the problem. Astronomers have identified 3 partial explanations that could each reduce the tension somewhat without requiring new physics. The first is that star formation in the early universe was simply more efficient than it is today. Denser gas, more frequent collisions between gas clouds, conditions that allowed more of the available hydrogen to collapse into stars before anything could stop it. The second is that actively feeding black holes at the centers of some of these early galaxies were contributing to the apparent brightness, making galaxies look more massive than their stellar populations alone would justify. The third is a timing effect. Brief, violent episodes of star formation are intrinsically bright, and a survey that catches a galaxy during such an episode will overestimate its typical mass. Each of these explanations is physically reasonable. None of them, individually or together, fully accounts for what Webb has observed. The residual discrepancy, after corrections for all 3 effects, remains. The difference may lie in how the early universe handled stellar feedback. In the modern cosmos, the death of massive stars is self-limiting. Supernova explosions and the radiation from young, hot stars drive gas outward from galaxy centers before it can form more stars, damping the rate of formation. In the denser, more turbulent conditions of the early universe, that feedback may not have operated with the same efficiency. More gas may have reached the threshold for collapse before anything could stop it. The architecture of the early universe may simply have permitted things to build faster. Whether that is enough to explain what Webb has seen is a question the community is still working through. And the finding is not a fluke. It appears in the data from the survey that first revealed Labbé's candidates. It appears in the deep fields targeted by the JADES program. It appears in the wide area survey known as Uncover. 3 independent surveys, different parts of the sky, different instruments, consistent results. The standard model said the early universe should have been quiet. Webb keeps finding that it was not. Knowing that galaxies were appearing too early and too massive was not the same as knowing how far back they went. For that, a different kind of program was needed, one willing to commit enormous amounts of telescope time to a single question. That program was called the JADES Survey, designed before Webb launched by Brant Robertson at the University of California, Santa Cruz, and Daniel Eisenstein at the Harvard Center for Astrophysics. They chose where to look carefully, the field directly adjacent to the Hubble Ultra Deep Field, the same patch of sky that Hubble had observed more deeply than almost anywhere else in the universe. The reason was strategy. Decades of Hubble observations had established what that region looked like in visible light. Webb would show what it looked like in infrared, and the comparison would be immediate. The program required two things in sequence. The first was photometric imaging, measuring each object's brightness across multiple infrared wavelengths. Photometry is fast. A single campaign can characterize thousands of galaxies in hours. By reading the colors, and particularly the sharp drop in brightness where neutral hydrogen absorbs incoming light, astronomers can estimate how far away a galaxy is. The estimate is not always right, but it narrows the field. The second was spectroscopy, spreading a galaxy's light into its full spectrum and reading it directly, identifying the precise emission features that confirm the true distance. Where photometry estimates, spectroscopy confirms. A single galaxy at extreme redshift may require dozens of hours of exposure. The program knew this. It committed the time anyway. The first JADES photometric data arrived in the summer of 2022. Candidates appeared, objects whose colors suggested redshifts of 12, 13, even 14. Some held up, others did not. Emma Curtis Lake at the University of Hertfordshire led the spectroscopic follow-up. In early 2023, she confirmed 4 galaxies at redshifts ranging from 10.3 to 13.2, placing the most distant of them 320 million years after the Big Bang, the first time any galaxy that early had been confirmed with genuine spectroscopic certainty. Curtis Lake said she had been waiting decades for exactly this capability, and that achieving it within the first few months of Webb's operation had been extraordinary. Among the photometric candidates that could not yet be confirmed was one that kept drawing attention. It sat at an extreme end of the redshift distribution. Estimates suggested it might lie at redshift 14, but it appeared in the imaging uncomfortably close to a foreground galaxy, and the blending made any measurement uncertain. The team looked at it. They debated. They decided it was worth pursuing. In October 2023, the JADES program committed 5 full days of imaging time to building the deepest infrared image ever made of that region. You are waiting as the decision is made. You are waiting as the exposures accumulate across 5 days of orbital time. The image that comes back is the deepest infrared view of that sky ever produced. The candidate is there, resolved and real, was separated clearly from its neighbour. In January 2024, the spectroscopic campaign began. 75 hours of time through Webb's spectrograph, trained on a single object. The result was redshift 14, 290 million years after the Big Bang. To feel the weight of that number, a galaxy at redshift 14 has had its light stretched by a factor of 15 during its journey. What left as ultraviolet, energetic, short wavelength, arrived at Webb as infrared. The universe transformed the light in transit. The galaxy, now confirmed as the most distant ever observed and designated JADES GS Z140, is over 1,600 light-years across. That matters. A single luminous object, a quasar, an actively feeding black hole, can produce enormous quantities of light from a tiny region of space. At 1,600 light-years across, this is not that. The light must be coming from stars, distributed across a genuinely extended galaxy. Stars that had formed, assembled into a coherent structure, and were burning together in numbers large enough to be seen from 13.5 billion light-years away. Stefano Carniani at the Scuola Normale Superiore in Pisa led the team that confirmed the discovery. He wrote in the paper that it was stunning that the universe could make such a galaxy in only 300 million years. Then came the detail that compounded everything. Jacob Helton, working at the University of Arizona, I examined what happened when he looked at the galaxy through the mid-infrared instrument, the coldest of Webb's 4 scientific instruments, the one sensitive to the longest wavelengths. The galaxy appeared at 7.7 micrometers. That wavelength corresponds to emission from hydrogen and oxygen, shifted there by the galaxy's extreme redshift. Oxygen. Oxygen does not exist at the beginning of the universe. It is not a primordial element. It is produced inside stars, forged in the nuclear reactions that power them through their lives, and released into the surrounding gas when those stars die. The oxygen in Jade's GS-Z140 means that stars had already formed inside that region of space, burned through their fuel, and exploded, all before the galaxy we are observing even existed in recognizable form. And an entire stellar generation had lived and ended before 290 million years after the Big Bang. Peter Van Dokkum at Yale University put it directly. You go from nothing to these fully formed galaxies, he said, in the blink of an eye. Jade's GS-Z140 is not an isolated anomaly. Every time deep surveys have pushed to the earliest epochs, they have found more than expected. More galaxies, more structure, more chemical complexity. The record will almost certainly be broken again. But the record is not the point. The point is what these objects reveal about a universe that was already building, already chemically enriched, already far further along than any model predicted at a time when it had barely begun. And those stars that had already lived and died before the galaxy came into view, the generation that left oxygen as their signature, were not the first. Something had come before them, something that has never been directly observed. Before there were galaxies, before there were stars, before any light existed anywhere in the universe, there was a period of genuine and total darkness. After recombination, after the universe cooled enough for atoms to form, and the light imprisoned in the hot plasma was finally released, the cosmos entered an era that cosmologists call the cosmic dark ages. The matter filling the universe was neutral. No nuclear fusion had begun anywhere. No photon was being produced. The universe was cold, dark, and silent, threaded only by the slow gravitational accumulation of gas into the halos that dark matter had already begun to build. For perhaps 100 million years, nothing shone. Gravity was patient. Gas, overwhelmingly hydrogen, with a fraction of helium and almost nothing else, was being pulled gradually into the densest regions. The clouds grew, and eventually, in some of those clouds, the pressures and temperatures at the center reached a threshold. Hydrogen nuclei began to fuse. The first stars ignited. They were nothing like the stars that exist today, and the reason for that comes down to a single word: cooling. For a gas cloud to collapse into a star, it has to shed energy. A cloud that cannot cool cannot collapse efficiently. It sits at a temperature that resists compression. In the modern universe, the most efficient cooling pathways involve elements like carbon and oxygen, which radiate energy away quickly. But in the early universe, there was no carbon, there was no oxygen, there was no iron, no nitrogen, no element heavier than helium except trace lithium. The only cooling mechanism available was molecular hydrogen, two hydrogen atoms bonded together, capable of shedding energy, but slowly and only under specific conditions. The consequence was unavoidable. Gas that cools slowly cannot fragment into small pieces. It forms massive clouds instead, and massive clouds collapse into massive stars. The physics of cooling in that metal-free environment was the physics of stellar mass. The first stars were almost certainly far larger than anything that exists in the universe today. Perhaps tens of solar masses, perhaps hundreds, but perhaps, in the most extreme cases, thousands. The term Population 3 was introduced by the astronomer Neville Wolfe in 1965 to describe this hypothetical first generation of stars, objects formed from gas containing only the elements present at the end of the Big Bang. No carbon, no oxygen, no iron, just hydrogen, helium, and a trace of lithium, compressed by gravity until nuclear fire began. None of them have ever been directly observed. They burned through their fuel at a rate proportional to their mass, and because they were so massive, they burned fast. A star 60 times the mass of the Sun exhausts its hydrogen in less than 1 million years. Population 3 stars may have been far more massive than that. They ignited, blazed, and died before the Milky Way took its present shape, and before the solar system formed. Their lifetime's geological instants on the scale of cosmic time. Some of them died in an unusual way. Stars above roughly 130 solar masses are theorized to undergo a catastrophic process in their final moments. As the core burns hotter and hotter, the gamma rays it produces become energetic enough to spontaneously convert into pairs of electrons and positrons, particles that carry energy away without contributing to the pressure that was holding the star up. The loss of that radiation pressure triggers a sudden collapse. The star does not simply explode outward like a standard supernova. It detonates entirely, releasing all its energy in a single violent event, leaving no remnant behind. No neutron star, no black hole, just a bloom of heavy elements dispersed into the surrounding gas. This matters because of what it tells us about what those first stars left behind. Some Population 3 stars left compact remnants, others left only chemistry, and it is the chemistry that Webb has begun to find. In a galaxy designated GS3073, seen at a redshift of 5.55, roughly 1 billion years after the Big Bang, Devesh Nandal at the University of Virginia and the Center for Astrophysics at Harvard and the Smithsonian identified something that could not be explained by any combination of ordinary stars. The ratio of nitrogen to oxygen in that galaxy was extreme, not slightly elevated, not at the edge of what known stellar populations can produce, and so far beyond any standard explanation that Nandal and his collaborators were forced to model something entirely different. Stars of 1,000 to 10,000 solar masses, objects that dwarf anything in the present universe, objects of the kind that Population 3 theory had long predicted. When they ran the models, those stars reproduced the observed chemical abundances. This is not a direct detection of Population 3 stars. No telescope in existence can observe objects that burned and died more than 13 billion years ago. What it is, instead, is the first confirmed chemical fingerprint of that generation at cosmological distance, the mark left on the gas and the galaxies that came after them, the residue of fires that burned before anything else in the universe existed. The evidence is not only in distant galaxies. Our own galaxy carries it too. Among the oldest stars in the Milky Way, ancient, metal-poor objects whose chemistry reflects the conditions under which they formed. There are stars that appear to have been born from gas seeded by population 3 supernova. Stellar archaeology, conducted in our own backyard, connects those distant Webb observations to objects visible in a moderate-sized telescope on a clear night. The earliest chapter of cosmic history left its handwriting in the stars that survive today. When population 3 stars ignited, they did something beyond simply shining. Their radiation, intense, energetic, ultraviolet, poured outward into the surrounding hydrogen gas and began to change it. The universe that had been opaque and neutral for 100 million years started, slowly and then all at once, to become something else. The radiation from those first stars did not simply illuminate the universe, it rewrote it. Where ultraviolet light struck neutral hydrogen atoms, it knocked electrons free, a process called ionization. Around each young massive star, a small bubble of ionized, transparent gas began to form. Around each cluster of stars, the bubble grew larger. The clusters gathered into the earliest galaxies, and around each of those galaxies, the bubble expanded further, reaching out into the surrounding fog of neutral hydrogen that had filled the cosmos since recombination. For hundreds of millions of years, the bubbles grew and multiplied. They merged with their neighbors. They overlapped and expanded until eventually, the neutral hydrogen between galaxies was gone. Stripped of its electrons, it converted from an opaque fog into the transparent medium that the cosmos has been ever since. Astronomers call this the epoch of rionization, and it is the last time the fundamental state of ordinary matter throughout the universe changed. Knowing that it happened is one thing. Knowing when and how fast, and driven by what. Those are harder questions. And Webb, combined with a completely different kind of telescope, is beginning to close in on answers that do not entirely match what was expected. The first way to measure reionization is to look through it. Quasars, the luminous cores of actively feeding galaxies, bright enough to be detected across billions of light years, provide a natural backlight. Their light passes through all the gas between them and us, and neutral hydrogen leaves a specific mark on it. There is a wavelength of ultraviolet light, known as the Lyman alpha wavelength, that energetic stars produce in abundance and that neutral hydrogen absorbs almost completely. When the intervening gas is neutral, that Lyman alpha light vanishes before reaching us. Astronomers call the resulting gap in the spectrum the Gunn-Peterson trough, after James Gunn and Bruce Peterson, who predicted this signature in 1965. Observations of quasars at high redshift show exactly this. Beyond redshift 6, before roughly 1 billion years after the Big Bang, quasar spectra show the complete absorption that Gunn and Peterson predicted. The gap is there. The universe at that epoch was full of neutral hydrogen. Below redshift 6, the signal vanishes. The fog is gone. Rionization was complete. That placed the end of rionization at roughly 1 billion years after the Big Bang. But Webb has been complicating that picture. One of the most striking single observations Webb has made in the context of rionization came from detecting a galaxy seen only 330 million years after the Big Bang, designated in the JADES catalogue as the object JADES GSZ131LA, that was actively leaking Lyman alpha photons into the space around it. This matters because Lyman alpha light does not normally escape from a galaxy surrounded by neutral hydrogen. The surrounding gas absorbs it immediately. For the light to escape, the gas around the galaxy must already be ionized. The galaxy was creating an ionized bubble roughly 650,000 light-years across, in the surrounding neutral fog, a region of transparency carved out by its own radiation, visible to Webb across more than 13 billion light-years of space. It is the earliest galaxy ever caught in the act of doing this. Julian Munoz at the University of Texas, Austin, examined what Webb's growing census of early galaxies implied for the timeline of reionization as a whole. The galaxy population Webb has revealed produces far more ionizing ultraviolet radiation than the standard model anticipated. When Munoz calculated how long it would take those galaxies to complete the work, the answer came back much earlier than 1 billion years. And between 550 and 650 million years after the Big Bang is when reionization should have ended, according to the revised accounting. That is a discrepancy of roughly 350 million years, meaning either the galaxy population is more efficient than assumed, or neutral hydrogen was recombining more frequently than models allowed, or both. Hakim Atek at the Institut Astrophysique de Paris found part of the explanation in the galaxies that are too faint to be individually characterized even by Webb. Objects at the extreme low end of the brightness distribution. His analysis showed that even those faint galaxies, when their contributions are added up, are producing ionizing photons at roughly 4 times the rate the standard model expected. The dimmest members of the early galaxy population are contributing more to the reionization budget than anyone had accounted for. The attempt to measure reionization from the opposite direction, not through the galaxies doing the ionizing, but through the neutral gas being ionized, is underway in the northern Cape of South Africa. The hydrogen epoch of reionization array is 350 radio antennas spread across the landscape, scanning the sky for the 21-centimeter radio emission that neutral hydrogen produces. That signal, stretched by cosmic expansion, carries a direct record of when and where the neutral gas existed. Mapping it would give a picture of how the fog lifted, from the perspective of the fog itself. The challenge is formidable. Josh Dillon at the University of California, Berkeley, who works on the analysis, has described trying to extract the reionization signal as similar to listening for the treble at a concert when the bass is 100,000 times stronger. The galactic radio background is overwhelming. Separating the signal from the noise requires an instrument and an analysis pipeline of extraordinary precision. Webb and the array are, in a sense, looking at the same event from opposite sides. One watching the sources of ionizing radiation, the other searching for the neutral gas being ionized. Their findings will eventually have to be consistent with each other. What they are both suggesting, right now, is that the timeline of reionization was compressed, that the early universe was ionizing its surroundings faster than the standard picture allowed. And the galaxies responsible were not the bright ones at the center of the distribution, they were everywhere. Those galaxies were not only ionizing hydrogen, at their centers, something was growing. Every black hole has an appetite, and every appetite has a limit. When gas falls toward a black hole, it does not drop straight in. It spirals, forming a disk of superheated material that releases enormous quantities of radiation as it compresses and heats. That radiation pushes outward, and outward means against the infalling gas that is trying to replace it. There is a rate at which the outward pressure of radiation exactly balances the inward pull of gravity on the surrounding material. Feed a black hole faster than that rate, and the radiation pressure wins, pushing gas away before it can fall in. Astronomers call this ceiling the Eddington limit, and it is not a minor technical constraint. It is the fundamental governor on how fast a black hole can grow. Consider what this means for the early universe. The first black holes were the remnants of massive stars, objects of tens of solar masses at the most. to grow from tens of solar masses to tens of millions of solar masses in less than 500 million years. A black hole would need to feed continuously at or near the Eddington limit for essentially the entire period. No interruptions, no pauses, no mergers disrupting the gas supply. Sustained accretion at maximum rate for 500 million years without pause. That is physically extreme. And yet the evidence suggests it may not be extreme enough to explain what Webb has been finding. Throughout Webb's deep surveys, a class of objects began appearing that had not been predicted in the numbers or characteristics they were seen. Astronomers called them little red dots, compact, luminous, distinctly red sources scattered through the early universe. As spectroscopic follow-up accumulated, many of them were confirmed as actively feeding black holes, already massive, already shining with the energy of material spiraling inward. They appear in larger numbers than models had anticipated. Their properties suggest that either standard growth models are missing something, or these black holes did not grow in the way the standard picture describes. Roberto Maiolino, working at the Kavli Institute for Cosmology at the University of Cambridge, led studies of several of these objects. Among the earliest confirmed examples was one found at a redshift of 10.6, barely 400 million years after the Big Bang, whose host galaxy already showed signs of chemical enrichment that implied a long history of star formation. The black hole at its center was already enormous. The galaxy around it was already mature. Both of them had assembled faster than anyone expected. Then came UHZ1. Akos Bogdan, at the Center for Astrophysics at Harvard and the Smithsonian, used a method that combined two completely different observatories to locate it. The galaxy cluster, Abell 2744, sits between Earth and a population of objects at much higher redshift. Like all massive concentrations of matter, it bends and magnifies the light from those background objects, a gravitational lens, and Bogdan used this natural magnification to bring into focus sources that would otherwise be too faint to study, turning both the James Webb Space Telescope and the Chandra X-ray Observatory on the magnified background population. UHZ1 is a galaxy at redshift 10.1, 470 million years after the Big Bang. When you look at its properties, the black hole at its center has a mass of roughly 40 million solar masses. The galaxy surrounding it has a total stellar mass comparable to that figure. The black hole does not sit at the center of a vast stellar system, a compact engine at the core of something much larger. It is as massive as the galaxy itself. The two are comparable in mass. Standard models of galaxy formation do not produce this. Priyamvada Natarajan at Yale University had been developing a theoretical framework to explain objects like UHZ1 for years before Webb was launched. Her work focused on what she called overmassive black hole galaxies, systems where the central black hole formed not through the gradual accumulation of mass from a stellar remnant, but through the direct collapse of a massive cloud of primordial gas, bypassing stars entirely. In her model, a gas cloud under the right conditions, dense enough, hot enough, sufficiently shielded from the radiation that would otherwise cause it to fragment, collapses directly into a black hole seed of millions of solar masses. No stars, no intermediate steps, gas, then black hole, in one catastrophic event. When UHZ1's observed properties were compared against the predictions of direct collapse models, the match was striking. The mass, the luminosity, the ratio of black hole mass to stellar mass, all of them fell within the range that Natarajan's framework predicted for objects formed this way. The community is not unified on a single explanation. three mechanisms remain in serious contention. The first is that population 3 stellar remnants, the compact objects left behind by the most massive early stars, could, under specific conditions, grow faster than standard models allow. The second is direct collapse, as Natarajan's framework describes. The third is super-Eddington accretion, a possibility that the Eddington limit, for all its authority, is not an absolute ceiling. Under certain conditions of geometry or radiation transfer, it may be possible to feed a black hole faster than the standard calculation permits. Current physics does not rule this out. No model of any of these three mechanisms fully accounts for all the objects Webb is finding. What all three mechanisms share is an implication that challenges something deeper than the models of black hole growth. The conventional picture of cosmic structure has galaxies forming first, dark matter, halos gathering gas, stars igniting inside them, and the central black hole growing gradually inside the galaxy over billions of years, a relatively minor component of a much larger system. What UHZ1 and the other overmassive black hole galaxies suggest is that in at least some cases, this sequence may be inverted. The black hole came first. The galaxy grew around it. If that is true, and the evidence is accumulating that in the earliest epochs it may have been, then the relationship between black holes and galaxies is not what we thought. The black hole is not a product of galaxy formation. It is a precondition for it, and everything that follows from that depends on the universe being far more complicated at far earlier times than the standard picture was ever designed to accommodate. Here is a reasonable assumption. The universe is 13.8 billion years old. Light travels at a finite speed. Therefore, the most distant objects we could possibly observe must lie no more than 13.8 billion light-years away, since light from anything further simply would not have had time to reach us yet. This is the obvious conclusion. It is also wrong. The observable universe extends to a radius of approximately 46 billion light-years in every direction, a total diameter of roughly 93 billion light-years. The universe is not 13.8 billion light-years across. It is 3.5 times larger than that. And understanding why requires returning to something established early in this video and pushing it further than we did there. Light travels at a fixed speed through space, but space itself is not fixed. It expands. And it has been expanding the entire time that ancient light has been traveling toward us. The galaxy, whose photons are reaching us now, was far closer when it emitted that light than it is today. The photon left, began crossing the universe, and while it was in transit, the space through which it was traveling continued to stretch. The galaxy moved further away. The photon chased a moving target across a growing medium. Think of a ship crossing an ocean where the ocean itself is expanding. The ship moves at its own speed through the water, but the water is spreading apart beneath it, carrying the far shore further away with every passing moment. When the ship finally arrives, it has crossed a distance greater than its own speed, multiplied by its travel time would suggest, because the destination was retreating as it traveled. Light is that ship. Space is that ocean. And the galaxy it came from is a shore that has been receding since the moment the photon departed. This is why the observable universe is larger than the naive calculation predicts. The photons that reach us from the most distant detectable sources have been traveling for 13.8 billion years. But the sources they left are now 46 billion light-years away, because space expanded throughout the journey. The mathematical framework that makes these distances calculable was developed in 1922 by a Russian mathematician named Alexander Friedmann. Working from Einstein's general theory of relativity, which describes how matter and energy curve the geometry of space-time, Friedman derived a set of equations that describe how the expansion rate of the universe changes over time, depending on what the universe contains. Different amounts of matter, radiation, and dark energy produce different expansion histories, and each expansion history implies a different relationship between a galaxy's observed redshift and its actual distance from us. Every distance measurement in cosmology, every figure that places a galaxy 400 million or 2 billion or 13 billion years back in cosmic history, is ultimately derived from Friedman's equations applied to measurements of what the universe contains. They are the foundation beneath all of it. Those equations also describe a universe that could be far larger than the portion we can observe. And another piece of physics suggests exactly that. In January of 1981, a physicist at the Massachusetts Institute of Technology named Alan Guth published a paper proposing that the universe had undergone a brief but extreme episode of accelerating expansion in the first tiny fraction of a second after the Big Bang, so brief that expressing it in ordinary time units requires scientific notation, and so violent that the universe increased in size by an extraordinary factor in almost no time at all. This process is called inflation, and it was driven not by any force we can directly detect today, but by the energy of a quantum field in a high-energy state that rapidly decayed. The consequences of inflation are profound and far-reaching. Before inflation, the region of space that would eventually become the observable universe was small enough and had existed long enough for all parts of it to be in thermal contact with each other. Everything within it had reached the same temperature. Then, inflation stretched that region to cosmological scales, preserving that uniformity across a volume far larger than causal contact could have established if expansion had been slower. This is why the cosmic microwave background looks the same in every direction to 1 part in 100,000, a uniformity that would be deeply puzzling without inflation to explain it. And inflation implies that the universe extends far beyond the edge of what we can see. The region that inflated into the cosmos we observe today was a tiny fraction of what existed before inflation ended. Everything beyond the horizon of our observation is, in all probability, more of the same physics, the same dark matter halos, the same galaxies forming and dying, governed by the same laws, simply out of contact with us in both directions. That horizon is not a wall. Nothing marks it physically. An observer anywhere within the universe would see their own version of it, a sphere centered on themselves, bounded by the distance that light has had time to cross since the Big Bang. Beyond that sphere, events are happening. Galaxies exist. Stars ignite and exhaust their fuel. But no signal from those events has yet had time to reach us, and no signal from us has reached them. The extreme uniformity of the cosmic microwave background is the evidence that this is true. Temperature identical to 1 part in 100,000 in every direction. A smoothness that would be statistically impossible if the universe simply ended at the edge of what we can see. The universe is smooth beyond our horizon because it continues beyond our horizon. No telescope built on any physical principle will ever see past it. What Webb can see is everything within it, and it has been finding, within those boundaries, a universe far richer and more populated than anyone expected. Point Webb at a region of sky that looks entirely empty. Not faint, empty. A patch of sky with no stars visible to the naked eye. No galaxies resolvable through a typical ground telescope, just darkness. Hold it there for hours, accumulating photons one by one. letting the detector build up what no single glance could reveal. What emerges from that accumulation is not emptiness at different depths, it is structure. Dense layers of galaxies appear, stacked at different distances from us, each layer a different moment in cosmic time. Galaxies from 2 billion years after the Big Bang sit behind galaxies from 5 billion years back, which sit behind galaxies from 9 billion years back, all compressed into a single field of view. The darkness was not empty. It was full of light too faint to see without patience. This is what Webb does, and it has done it across many regions of sky. The picture that results is not just deeper than what came before. It is a different kind of picture, one that includes populations of galaxies that previous instruments could not detect at all. For decades, the best estimate for the total number of galaxies in the observable universe came from Hubble's deep field observations. The figure that emerged from those surveys was somewhere between 100 billion and 200 billion galaxies, an extraordinary number, and already far beyond intuitive comprehension. Webb has complicated that estimate. Its ability to detect fainter objects, particularly in the infrared wavelengths that the most distant and dusty galaxies emit most of their light in, reveals populations that Hubble simply could not see. The current estimate, accounting for everything Webb is detecting and modelling the populations that remain below even its detection threshold, puts the true number of galaxies in the observable universe at potentially several trillion. Several trillion galaxies, each containing hundreds of billions of stars, many of those stars likely hosting planetary systems of their own. The numbers are too large to hold in the mind, and they describe only the observable fraction of what exists. Across that vast population, the distribution of matter is not random. Look at the universe on large enough scales and a pattern emerges. A three-dimensional network of filaments and nodes, and vast empty spaces between them. Galaxies cluster along the filaments. Where filaments intersect, clusters of galaxies accumulate. Between the filaments, spanning distances of hundreds of millions of light years, enormous voids extend in every direction, containing almost nothing. This structure is called the cosmic web, and it is not a theoretical construct. Webb and its predecessors have mapped it directly. The filaments are real, the voids are real, and neither is an accident. The Cosmos Webb survey was designed to map this structure with a precision that no previous infrared survey had achieved. Led by Jehan Kartal-Tepe at the Rochester Institute of Technology and Caitlin Casey at the University of Texas, Austin, it is the largest contiguous infrared survey ever conducted at space-based resolution, covering 2.5 square degrees of sky and capturing hundreds of thousands of individual galaxies across a broad range of cosmic epochs. The sheer volume of data it has produced has made possible something that had not been done before: a comprehensive statistical picture of galaxy populations across cosmic history, observed simultaneously in the wavelengths that reveal their earliest and most obscured phases. Within that survey, Diana Sconomilio at the Jet Propulsion Laboratory used a technique called weak gravitational lensing to build something even harder to achieve: a map not of the galaxies themselves, but of the dark matter scaffolding that holds them in place. Gravity bends light. When light from distant background galaxies passes near a foreground mass, visible or invisible, the shapes of those background galaxies are slightly distorted, stretched and sheared in patterns that reflect the distribution of the mass doing the bending. No individual distortion is detectable. Galaxies come in irregular shapes to begin with, but when you measure the shapes of hundreds of thousands of galaxies and look for statistical patterns in those distortions, the signal of the dark matter between us and them becomes legible. The mass reveals itself through what it does to the light behind it. Scognamiglio's analysis detected dark matter filaments extending out to 5 billion light-years, with a density of over 129 galaxies per square arc-minute, used as tracers of the underlying mass. It is, in effect, a map of something invisible, drawn by using visible things as probes. The cosmic web exists because of processes that began in the first fraction of a second of cosmic history. Inflation seeded tiny fluctuations in the density of the early universe. Quantum variations, magnified to cosmological scales. Dark matter, which responds only to gravity and not to the electromagnetic forces that affect ordinary matter, began flowing toward those overdense regions first. Over hundreds of millions of years, dark matter halos assembled. Ordinary matter fell into those gravitational wells, cooled and collapsed further. Galaxies ignited inside the halos. What Webb observes today as the cosmic web is the visible imprint of that gravitational history, the pattern that dark matter laid down before any star existed, made visible by the galaxies that grew along it. The voids are as important as the filaments. They are not truly empty, sparse populations of dwarf galaxies and diffuse gas thread through them. But their near emptiness is what makes the structure of the web legible. The contrast between dense filaments and nearly empty voids is the signature of a universe shaped, from its earliest moments, by something that cannot be seen. What that something actually is has been one of the deepest questions in physics for nearly a century. The evidence for its existence is overwhelming. The identity of the particle or field that constitutes it remains unknown. In 1933, a physicist studying the Coma cluster applied a straightforward calculation to an observation that had been troubling him. He was measuring how fast the galaxies within the cluster were moving. From those velocities, he could calculate how much gravitational mass the cluster needed to contain to hold itself together. The answer he got was roughly 500 times larger than the mass of all visible matter in the cluster. Every star, every cloud of gas, every observable source of light, added together accounted for less than 0.1% of what the calculation required. He published. His colleagues found alternative explanations, or more often, simply moved on to other things. His name was Fritz Zwicky, and the problem he had identified would go unresolved for 4 decades. The idea itself was not forgotten. It persisted at the margins of astrophysics, occasionally revisited and occasionally dismissed, waiting for evidence strong enough to compel attention. That evidence arrived at Kitt Peak National Observatory in Arizona in 1968, in the form of a measurement that Vera Rubin and Kent Ford had set out to make for entirely different reasons. Rubin and Ford, working at the Carnegie Institution of Washington, were measuring the rotation curve of the Andromeda Galaxy, how the orbital velocities of stars change with their distance from the center. The prediction was well established. Stars near the edge should orbit more slowly than those near the center, just as the outer planets orbit more slowly than the inner ones. More of the galaxy's mass lies inside a central star's orbit than an outer one's, so the outer star feels weaker gravity. What Rubin and Ford found was that this did not happen. The rotation curve was flat. Stars at the outer edges of Andromeda were orbiting at essentially the same speed as stars much closer to the center. The curve that should have declined with distance simply did not decline. Rubin spent months trying to find an error. There was no error. What the data required was that the mass of Andromeda did not drop off with distance from the center in the way the visible matter did. The galaxy was embedded in a much larger distribution of unseen mass, a vast halo extending well beyond the luminous disk. providing the gravitational pull that kept the outer stars moving at the velocities the data showed. The mass was not where the light was. Over the following years, Rubin and Ford measured the rotation curves of more than 75 spiral galaxies. The result was the same every time: flat. The outer stars always moved too fast. By the early 1980s, dark matter had moved from Zwicky's ignored calculation to a central pillar of cosmology. It constitutes roughly 85% of all matter in the universe. Everything visible, every star, every planet, every gas cloud, accounts for approximately 15%. The identity of the particle or field responsible for this invisible mass has remained unknown ever since. The leading candidate for much of the late 20th century and into the 21st was a class of hypothetical particles known as weakly interacting massive particles, particles that would interact with ordinary matter through the weak nuclear force and gravity, but not through electromagnetism, making them effectively invisible to any instrument that detects light. Decades of experiments searched for them with increasing sensitivity. None found them. The most recent and most precise of those searches was conducted nearly a mile underground at the Sanford Underground Research Facility in South Dakota, inside the tunnels of a former gold mine, deep enough to shield the detector from cosmic rays that would otherwise swamp the signal. The active volume held 10 tons of ultra-pure liquid xenon at cryogenic temperature. Between March 2023 and April 2025, the experiment accumulated 417 live days of data. The result was no detection. No weakly interacting massive particles were found in the mass range between 3 and 9 giga-electron volts. Rick Geitskell at Brown University, who has spent his career building experiments of this kind and who serves as the collaboration's spokesperson, noted that the detector is now more than 3 million times more sensitive than the instruments available when he entered the field. Alvine Kamaha at the University of California, Los Angeles, and her colleagues on the collaboration noted that the experiment is now operating in what they called discovery territory, a region of sensitivity that no previous detector had reached. Discovery territory, and still nothing. A null result is not a failure. Every experiment that finds nothing rules out a region of the parameter space that physicists use to describe what dark matter might be. Each null result narrows the possibilities. The question is not whether dark matter exists. The gravitational evidence accumulated since Zwicky's calculation is overwhelming and comes from dozens of independent lines of observation. The question is what dark matter is. Weakly interacting massive particles may not be the answer. One leading alternative is a class of particles called axions, originally proposed not to explain dark matter, but to solve a separate problem in the physics of the strong nuclear force. Axions would be extraordinarily light and interact through a different mechanism entirely, while requiring a different detection strategy. A precisely tuned resonant cavity in a powerful magnetic field, scanning for the faint signal produced when an axion converts to a microwave photon. An experiment at the University of Washington has been searching this way for years. No detection yet. On a mountainside in Chile, something else is underway. The Vera C. Rubin Observatory, named for the scientist whose measurements did more than anyone else's to establish the case for dark matter, began its survey of the southern sky in 2025. Scanning the entire southern hemisphere every few nights for 10 years, it will produce the most comprehensive map of dark matter ever assembled, derived from the gravitational lensing signatures of billions of galaxies. Rubin's work, continued by an institution that carries her name. But the dark matter is there. It holds together every galaxy, every cluster, every filament of the cosmic web. What it is made of remains the question. The gravitational evidence for dark matter is overwhelming, but gravitational evidence is, by its nature, indirect. It tells you that something is there, not what that something is, and it requires inference from the behavior of visible objects. What the bullet cluster provides is something different. It is not an inference, it is a separation. Gravity bends light. When light from a distant background galaxy passes near a large foreground mass, visible or not, the apparent shape of that background galaxy is distorted. Individual galaxies come in too many irregular shapes for any single distortion to be meaningful. But across a population of thousands, with the statistical patterns in those distortions reveal the mass distribution of whatever lies between us and them, including mass that emits no light at all. The technique requires no assumption about what dark matter is. It needs only one property: mass bends light. Apply this technique to a galaxy cluster at a moment of collision, and you get a controlled experiment that nature has performed for us. The object appeared in X-ray surveys as an unusually hot cluster. Maxim Markovich at the Chandra X-ray Center looked at it more closely and found not a single hot cluster, but the aftermath of something more dramatic. Two galaxy clusters that had passed through each other at high speed, leaving behind a bow-shaped shockwave of superheated gas, a bullet of compressed plasma trailing behind the smaller subcluster as it emerged from the encounter. The collision had occurred roughly 150 million years before the light we observe was emitted. The clusters lie 3.8 billion light-years away. What makes this collision so important for dark matter is what happened to the different components when they met. Galaxy clusters contain three distinct types of matter. There are the individual galaxies, each one a system of hundreds of billions of stars, separated from its neighbors by such enormous distances that galaxy-to-galaxy stellar collisions essentially never happen. There is hot gas, diffuse plasma spread throughout the cluster volume, vastly more massive than the stars it surrounds, and uncharged, meaning it interacts through electromagnetism. And there is dark matter, present in quantities that dwarf both, interacting with nothing through electromagnetism, feeling only gravity. When the two clusters collided, the three components behaved differently. The galaxies pass through largely unimpeded. Their separations are so vast that individual stellar collisions essentially never occur. The hot gas was not so fortunate. As the plasma clouds met, electromagnetic interactions brought the gas to a near halt. It piled up between the clusters, compressed and heated until it blazed in X-rays. Dark matter, interacting only gravitationally, should have passed straight through with the galaxies, leaving the mass concentrations separated from the plasma. Douglas Clow at Ohio University mapped the gravitational mass distribution of the system using lensing, measuring how the shapes of thousands of background galaxies were distorted by the foreground mass. Markovich mapped the gas distribution using the Chandra X-ray Observatory. The two maps were produced independently by different measurement techniques, responding to different physical quantities. When the results were compared, published in 2006, the conclusion was unambiguous. The gravitational mass concentrations were centered on the galaxies, not on the gas between them. The mass had moved with the galaxies through the collision, exactly as dark matter theory predicted. The probability of this spatial separation arising by chance was 1 in 10 to the power of 15. Two independent measurements, one conclusion. The mass passed through the collision with the galaxies while the gas did not. This is direct observational evidence that dark matter behaves as a non-interacting component, not an inference from the dynamics of a rotating galaxy or a calculation from cluster velocities, but a visible separation, captured in two images produced by two different instruments measuring two different things. Webb has returned to the bullet cluster with new eyes. James G. at Yonsei University and the University of California, Davis and Sangjun Cha at Yonsei University led observations that use not only background galaxies as lensing probes, but also the intracluster stars, stars that were stripped from their host galaxies during the violence of the collision, and now drift freely through the cluster volume, unattached to any galaxy. Kyle Finner, a part of the team, described what Webb's images added directly. They dramatically improve what we can measure in this scene, he noted, including pinpointing the position of invisible particles known as dark matter. The intracluster stars prove to be reliable traces of the dark matter distribution, even in this extreme, dynamically turbulent environment. The bullet cluster is one object in one part of the sky, but what it demonstrates applies to the entire observable universe. Computer simulations modeling millions of dark matter particles interacting only through gravity consistently produce a filamentary large-scale structure, the cosmic web, strikingly similar to what galaxy surveys observe. The visible universe is not distributed randomly. It traces an invisible architecture that dark matter laid down in the first billion years after the Big Bang, before most galaxies existed, before most stars had formed. What Webb maps as the cosmic web is dark matter's web, illuminated by the galaxies that grew inside it. One tension within this picture remains unresolved. The standard cosmological model predicts that small dark matter halos should be common, numerous enough that large galaxies like the Milky Way should be surrounded by hundreds or even thousands of small dwarf satellite galaxies. Observations find far fewer than predicted. Stellar feedback, the radiation and explosions of massive stars suppressing star formation in the smallest halos, is the leading explanation. It is not a complete one. Webb is now building the census of faint early galaxies that will eventually constrain these models more tightly. Dark matter built the scaffold. Everything else grew along it. What it is made of is still, after nearly a century of evidence for its existence, entirely unknown. But there is another invisible component of the universe, one that behaves in a fundamentally different way, and one whose discovery came not from a calculation or a rotation curve, but from the light of dying stars at the edge of the observable universe. In 1917, Albert Einstein applied his general theory of relativity to the universe as a whole, and immediately faced a result he did not want. The equations described a cosmos that could not be static. Matter attracted matter, gravity pulled inward, and the universe should have been either expanding or contracting. Einstein believed it was neither. He believed it was eternal and unchanging, and so he modified his equations, adding a term he called the cosmological constant, a kind of mathematical counterforce that balanced gravity on the largest scales and held the cosmos in equilibrium. 12 years later, Edwin Hubble's observations of distant galaxies confirmed that the universe was expanding after all. The cosmological constant was unnecessary. Einstein reportedly described it as his greatest blunder and discarded it entirely. What he could not have known is what that constant, or something very much like it, actually was. Before that answer could be found, a different question had to be settled. If the universe was expanding, the most natural expectation was that its expansion should be slowing. Gravity acts on everything. Every galaxy pulls on every other galaxy, and the accumulated gravitational attraction of all the matter in the universe should be drawing things together, gradually breaking the outward motion that began at the Big Bang. The question in the 1980s and early 90s was not whether the expansion was decelerating. It was how much, whether enough to eventually reverse the expansion entirely and end in a cosmic collapse, or too little for that, but decelerating nonetheless. Two research teams set out to measure the deceleration directly. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, began in 1988. The High-Z Supernova Search Team formed in 1994, led by Brian Schmidt at the Australian National University, with Adam Rees at Johns Hopkins University directing the data analysis. The two groups were rivals. They knew each other's work, they used the same method, and they had every scientific incentive to find different answers, because the first team to establish a result would be the one that mattered. The method they shared relied on a particular class of stellar explosion. When a white dwarf in a binary star system accumulates enough mass from its companion to cross a critical threshold, the point at which the pressure holding the star together can no longer resist gravity, it detonates. The explosion reaches a consistent peak luminosity because the trigger is always the same critical mass. A known luminosity compared with an observed brightness gives the distance to the explosion. The distance compared with the redshift of the host galaxy reveals how fast that region of the universe was expanding at the moment of detonation. Enough of these measurements, at enough distances, map out the expansion history of the universe. Both teams observed the most distant supernova they could find. Both teams expected to see evidence of deceleration. What both teams found, independently and to their initial disbelief, was the opposite. The distant supernovae were fainter than expected. Not slightly fainter, measurably, consistently fainter across the whole population of distant events. If expansion were slowing, distant supernovae would be closer than a steady expansion model predicted, and therefore brighter. They were dimmer, and they were further away than they should have been. The expansion of the universe was not slowing, it was speeding up. Both teams announced their results in 1998. Science magazine named the discovery Breakthrough of the Year. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. Whatever is causing the acceleration has been given the name dark energy. It does not emit light. It does not absorb light. It does not reflect light. It cannot be detected by any instrument that responds to electromagnetic radiation. Its existence is inferred entirely from what it does to the expansion rate of the universe, an acceleration that the equations of general relativity say must be driven by something with negative pressure, something that pushes outward rather than inward, something that constitutes approximately 68% of the total energy content of the cosmos. Its physical nature remains completely unknown. One framework places dark energy as Einstein's discarded constant, restored. In this view, empty space has an intrinsic energy density, a property of the vacuum itself, unchanging as the universe expands. Quantum field theory supports this interpretation in a sense, predicting that the vacuum of empty space is not truly empty, but seethes with virtual particle fluctuations, pairs of particles briefly appearing and annihilating in ways that contribute a real energy to space itself. The difficulty is the size of the prediction. Quantum field theory's estimate for the energy density of the vacuum is roughly 120 orders of magnitude larger than the cosmological constant as observed. This is not a small discrepancy. It is the largest gap between a theoretical prediction and an observation in the history of physics. Nobody knows how to resolve it, and it is the reason the nature of dark energy is considered the deepest open question in modern science. In March 2025, the Dark Energy Spectroscopic Instrument, a facility at Kitt Peak National Observatory in Arizona, operating 5,000 robotic optical fibers to measure the positions and distances of millions of galaxies, published its second major data release. The analysis found evidence, at a confidence level of 4.2 sigma, that dark energy may not be constant. Does the signal suggest that dark energy could be evolving over time, weakening as the universe ages, rather than maintaining a fixed density as the cosmological constant would predict? 4.2 sigma sits just below the 5 sigma threshold that the physics community conventionally requires to claim a discovery. If the signal strengthens as more data accumulates, it will demand the first fundamental revision to our picture of dark energy since Perlmutter, Schmidt, and Rees announced their results more than a quarter of a century ago. Einstein discarded his constant and called it his greatest blunder. The universe may have had other plans all along. Dark energy does not behave like anything else in the universe. Every other component of the cosmos, matter, radiation, the energy of stars and gas and dust, dilutes as the universe expands. Spread the same quantity of matter across a larger volume and its density falls. The gravitational influence it exerts per unit of space diminishes. Dark energy does not follow this rule. Its density appears to remain roughly constant as space grows. As the universe expands and creates more volume, more dark energy fills that volume. The more space there is, the more dark energy there is. The more dark energy there is, the faster the expansion accelerates. The faster the expansion, the more space is created. This is not a stable equilibrium. It is a feedback loop, and it operates on the scale of the entire observable universe. The consequences of this behavior have been unfolding for billions of years. Approximately 5 billion years ago, roughly when our solar system was just beginning to form, the density of dark energy surpassed the density of ordinary and dark matter combined, and its influence on cosmic expansion overtook theirs. Before that transition, matter dominated the dynamics of the universe on the largest scales. Gravity was the dominant force, galaxies were clustering, the cosmic web was consolidating, and new structure was forming at a rapid pace. After that transition, the picture changed. Accelerating expansion became the dominant fact of the universe on scales larger than individual galaxy clusters. The distances between clusters began growing at a rate that gravity could no longer overcome. The Webb had already been built. Now it was being stretched apart. Consider what this means for the current composition of the universe. Approximately 68% of its total energy content is dark energy. Approximately 27% is dark matter. Approximately 5% is ordinary matter. Every star, every planet, every atom in every creature that has ever lived. Everything we have ever seen, touched, measured, or imagined is a 5% rounding error in the true inventory of reality. Given that dark energy is constant, or very nearly so, the future of the universe follows from its current behavior in a straightforward way. Expansion continues indefinitely. On timescales of hundreds of billions of years, stars exhaust their nuclear fuel and go dark. Galaxies, unable to form new stars from the gas they have already expelled, gradually dim. Eventually, the only remaining sources of light are black holes, the accumulated remnants of dead stars, which glow faintly as they slowly consume whatever matter still falls into them. Even this ends. Black holes are not permanent. They slowly radiate their mass away through a quantum process over timescales, requiring a number larger than 10 to the power of 100 years. When the last one has gone, the universe is a cold, dark, nearly empty expanse where no thermodynamic process can occur and no structure can persist. This endpoint is called the heat death of the universe, and under the cosmological constant interpretation, it is the default long-term fate. But the cosmological constant interpretation may be wrong. If dark energy is not a fixed property of the vacuum, but a dynamical field, one whose density can change over time, then the possibility exists that it is not merely constant, but growing. A form of dark energy that increases in strength as the universe expands would produce consequences far more extreme than the slow fade of the heat death scenario. As the repulsive force grew, it would eventually overcome the gravity-binding galaxy clusters together. Then, individual galaxies, then solar systems, then atoms. Every bound structure in the universe dismembered, from the largest to the smallest. This scenario has been given the name the Big Rip. Current observations do not require a Big Rip. The evidence does not point to a dark energy that is growing stronger, but they do not rule it out either. The recent survey data suggesting that dark energy may be evolving adds a new layer of uncertainty, not necessarily toward a Big Rip, but toward a picture in which the cosmological constant may not be the final word. All of this unfolds across a span of cosmic time that is almost beyond comprehension. But it is worth noting where we sit within it. We exist at a moment when the universe is 13.8 billion years old enough for stars to have forged the heavy elements that make rocky planets and living things possible, but young enough that galaxies are still visible across the full extent of the observable universe. A billion years from now, some of what we currently observe will have receded beyond our horizon. Our moment, this precise moment in cosmic history, is the one in which the universe can be observed, measured, and understood in the way we have been describing across this video. That is not an assumption. It is a feature of where we are in time. There is a number at the heart of modern cosmology, a single measurement that every other cosmological observation eventually connects to. It describes how fast the universe is expanding right now, at this moment in cosmic history. Specifically, it describes the rate at which 2 points in the universe move apart from each other as a function of the distance between them. For every additional megaparsec, a distance of roughly 3.25 million light-years, any 2 points in the universe are currently moving apart at an additional velocity of some number of kilometers per second. That number is the Hubble constant. Right now, 2 of the most carefully conducted measurement programs in the history of astronomy are producing values for the Hubble constant that cannot both be correct. The gap between them is approximately 9%, and it has been getting wider, not narrower, as both programs have improved. The first measurement comes from the earliest epoch of the universe that any observation can access. The European Space Agency's Planck satellite spent 4 years, from 2009 to 2013, mapping the cosmic microwave background with extraordinary precision. The temperature fluctuations in that map are not random. They preserve the imprint of sound waves that propagated through the hot plasma of the early universe for the first 380,000 years of cosmic history, and before recombination froze them in place. The size and spacing of those waves encode the universe's composition at that moment, the amounts of ordinary matter, and dark energy present, and extrapolating from that composition to the present day, using the standard cosmological model, gives a Hubble constant of 67.4 kilometers per second per megaparsec. The second measurement comes from the local universe, the universe as it exists today. Adam Rees and a large international collaboration have spent years building what astronomers call a distance ladder, a series of calibrated rungs that carry distance measurements from nearby stars all the way out to the edge of the local universe. The first rung uses geometric parallax to measure the distances to Cepheid variable stars in the Milky Way, stars that pulsate with a period directly related to their luminosity, making them reliable distance indicators. The second rung uses those calibrated Cepheids in nearby galaxies to standardize Type 1a supernovae. The third rung uses those supernovae to measure the expansion rate directly across hundreds of millions of light years. The result? Approximately 73 kilometers per second per megaparsec. 67.4 versus 73. The gap between them, expressed in terms of the combined measurement uncertainties of both programs, now exceeds 5 sigma. In physics, 5 sigma is the conventional threshold for claiming a discovery. It corresponds to a probability of roughly 1 in 3.5 million that the discrepancy could arise from random chance. The Hubble tension, as it is known, is not a rounding disagreement or a matter of measurement precision. It is a genuine statistical crisis. Webb has made it worse. Rees used Webb to remeasure Cepheids in the same galaxies previously observed by the Hubble Space Telescope, but with far greater resolution and far less blending of light sources. The Hubble Space Telescope's images, at the distances involved, suffered from crowding, individual stars blending together in ways that could have systematically biased the brightness measurements. With Webb's sharper view, that bias could be assessed directly. The conclusion, published at 8.2 sigma confidence, was that photometric crowding had not been responsible for the higher local value. The leading systematic explanation for the tension, the most plausible route by which the local measurement could simply be wrong, had been tested and ruled out. Webb, rather than resolving the tension, sharpened it. Not everyone in the field is convinced that the local measurement is as clean as the distance ladder suggests. Wendy Friedman at the University of Chicago has spent decades working on cosmic distances, including her leadership of the Hubble Space Telescope Key project that first measured the Hubble constant to 10% precision in the early years of the 21st century. Her analysis using Webb, based not on Cepheids, but on tip of red giant branch stars, older, cooler, and more stable stellar markers that provide an independent distance scale, produces a value of approximately 70 kilometers per second per megaparsec. This sits between the Planck value and the Rees value. Friedman's interpretation is that systematic errors may still be embedded in Cepheid-based distance measurements that Webb has not yet fully revealed, and that the tension may partially dissolve as the different methods mature. The Hubble tension does not stand alone. There is a second tension, less dramatic, but pointing in the same direction. Weak lensing surveys of the large-scale structure of the universe consistently find that the cosmos is slightly less clumpy than Planck's measurements of the cosmic microwave background predict. The Hubble tension says the expansion rate is different from what early universe measurements expect. This second tension says the structure of the universe is different from what early universe measurements expect. Two independent measurements, two discrepancies, both pointing toward the same conclusion. Something about the late universe differs from the predictions of the standard cosmological model applied to early universe data. Physicists have proposed solutions. An episode of early dark energy, an additional energy component present in the universe before recombination, would have altered the scale of those frozen sound waves that Planck measures, raising the inferred Hubble constant from the cosmic microwave background data and reducing the gap. The Atacama Cosmology Telescope surveyed the microwave background with enough sensitivity to test this. It found no evidence for early dark energy. That resolution now seems less likely. What remains is the gap itself. Either systematic errors are hiding in well-scrutinized measurement methods that have now been checked repeatedly over decades, or the standard cosmological model is missing something real, and the expansion history of the universe between the Big Bang and today contains physics that no current theory has identified. Both possibilities are unsettling. Neither has been ruled out.